Okay, so the goal here is implementation of fault-tolerant atomic broadcast. There's a lot of adjectives used here. And so we're going to look at things in a rather narrow way. But we're doing this so that we also get some idea of what's going on in a more broad way. Okay? So let's go and first start off with fault tolerance. So fault tolerance, in English you might say it's ability to recover from unexpected situations. And given this definition, let's talk very broadly about what we might do in the real world to recover from unexpected situations. So of course, we're going to try to come up with the sketch of an algorithm to do the particular task that we have to finish. But I want to abstract out what we're doing there as much as I can. So I'm saying, okay, in English, you can talk about fault tolerance, about mistakes happening, and you want to recover from them. So what are some techniques at a very broad level that would also work in real world rather than just the computer world?
Having enough
Enough what?
Duplicates to be able to recover.
Duplicate, so give some real world task.
Yeah, like I'm thinking about like where you have enough information.
So lots of redundancy.
Or just have like a parity disk that just. Yeah.
So you're thinking computers already.
What's our failure model here? Are we saying like?
I mean, we're talking English. We're doing a little loose here, but our failure model here. Idea is that we can recover. Something bad happens. Something unexpected happens.
But is the something like we're all communicating over the telephone? And
Maybe.
Suddenly the telephone company decides to be evil and change our voices? Or is it like that one of us starts to try to lie to the others?
Yeah, that could be it. I mean, whatever unexpected.
Or one of us just dies. Like,
Okay.
which of those?
Yeah, so let's just say leaves the organization.
Okay.
That's a little better. So Chad leaves my TA leaves the organization. What do I do then?
Cancel all the homeworks.
Can't do all the homeworks. So if in 401 a TA leaves, how badly am I off?
How many TAs do you have?
That's the thing, right? So there's always this thing, the buck stops here, right? And what's the organizational chart? And they'd say, okay, this is the department head. If the department head is not around, the associate head makes a decision. Then full professors make it. So there's some redundancy. Okay, so that's you can have physical redundancy like 2 TAs. I remember when I was doing my thesis, the fire engines came to our department, and I said, oh my God, if there's a real fire, I am host. And after that, I started taking printouts home. This was before the disks and USBs and so forth, just so that so that's physical redundancy.
Of your code.
Of my thesis, I was more concerned about my words. So it took me longer to write the words than write the code. And other kinds of redundancy.
Shoot down if they haven't called Linda.
Sorry,
Forget the PhD.
I don't know what would have happened, but that made me think. It really made me think, and I started keeping copies at home and office of everything important. Before the cloud.
Dropbox does it all now.
Yeah. So that's physical redundancy. What else might you do? So parity bit, what's the example of that in real life?
Like storing information about your data so that if you're missing some of your data, you can recover that.
Yeah, so I don't know. It's like my handwriting is really bad, So when I send a letter, I better go and sort of duplicate. I don't know what the analog of parity. I mean, replication is fine, that you copy, you send, And if you ask me a question, I don't reply back, what do you do? Before the deadline, what would you do?
Send it again.
Send it again. Time redundancy, information redundancy, time redundancy, right? And then physical redundancy. Okay, so this is what we might do in general. Okay. Information redundancy is also there sometimes in real life, right? They will put it in capitals, or I repeat. He'll say, please do this by 5 o'clock. I repeat, do it by 5 o'clock. Right? So we see that in real life too. Okay. So now let's talk about distributed systems. So what kind of faults can we talk about in distributed systems?
Not failed.
Not failure. So that's what we're doing in our implementation. What else?
Byzantine.
So what is Byzantine failure?
One of the nodes gets hacked and starts being malicious.
Okay.
Sending purposefully wrong data.
So if you're supposed to be 5 Google servers somewhere around, all in sync, and one Google server is hacked, then suddenly it can confuse the other. Now it can confuse the other Google servers, and all our emails can get corrupted. Right? And that's the worst. That's called arbitrary failure, in fact. Other things?
An EMP,
Sorry?
electromagnetic pulse,
So
wipes out all the entire internet.
so information, so that's kind of covered by, the wrong answers being given. But so process dies, messages.
Lost.
Okay, the Google is fine, but the wires in between get tapped. Okay, so I'm not sure if this is exhaustive or not, but I had the student who did a paper on this last year, so I just got it from his write-up. These things: the crash failure, emission failure, and they talk about this in the literature. I've been looking at in the last 2 days. I've been looking at slides on fault tolerance, and they'll talk about this also. And timing failure does not respond in expected period, right? Timeout is a solution for that. And then there's arbitrary failure, unexpected response at an arbitrary time. Okay, so this is the Byzantine thing. Okay, so these are the various problems. Now, what about some general techniques? So information redundancy, yeah. So let's go and talk about that. What form will information redundancy take in a distributed system? Or can it take? I mean, again, this is not exhaustive.
Caching your information so that if someone is at not the right step, you can send them the old information.
So you're caching, or a cache means that you have a subset of the information.
Stored on multiple nodes.
So it's replicated.
Yeah.
Okay, cache means subset, replicated means the whole thing.
Well, I just meant, in our case, we are caching not the entire thing, but just up to some subset of the entire thing that is the last seen by anyone, the furthest seen by anyone.
That's a fault-tolerant algorithm. We are doing that, but a fault-tolerant algorithm assumes that all processes have the same state, right?
And like if one failed and it came back into the system, then you would need more than just that last bit of information, because you'd have to catch them all the way back up to date, or just tell them the current.
Okay, so there's how much you keep about the history of messages, and there's your current state also. But you're right. You're keeping. You certainly, the sequence number is the important part. That's replicated. Now, to do crash recovery, you might keep the whole data. You might keep some of the messages. Okay. So let's talk about Byzantine failure. How are we going to solve Byzantine failure? So we have a program with modules A, B, C, D. Right? A talks to B, B talks to C, C talks to D, and talks to A, and so forth. Each of these nodes can be captured. So what are we going to do now to tolerate this fault? Yeah, so we can have signatures, but they somehow get hacked, and they hack everything. I mean, so it's.
So.
But you're right. If we encrypt things well enough. Okay.
Yeah. Then we could also just try to detect unusual behavior.
Okay, so how do we know? This is okay. So we can do things like that. But we don't know whether I deleted the message myself or the terrorist deleted my message. Right. So, in general, if there are n nodes and all n get hacked, I mean, we are sunk, right?
Can we be a little more specific on exactly what we're trying
Yeah.
to do?
So Byzantine, we want to recover from Byzantine failure.
Sure, but what's the application? Like, what is recovering? Because, like, if it's consensus amongst all of the processes,
Yeah.
then some of them can just be, stubborn and not ever give the same value because they're in the Byzantine crash.
Right. So that's the whole point. So we have. So the point is
What's
that.
success?
So success is hopefully getting the right, the malicious guys.
So you could probe everyone, ask them the question, and if they respond correctly,
Well, I mean, the
then you could still
Bad guy could still
respond correctly. Yeah.
but like, so if we're all running the same thing and we're each doing the same calculation, then
Yeah, let's assume that.
then
Because that's what it's going
I
to
can
be.
just determine. I mean, I don't even have to query anybody else to know what the right answer is because I can just assume that I'm right, and then here's the
Okay,
thing I calculated.
so the whole idea is
I know I
that.
wasn't hacked.
So there's one Chad and there's another person, there's one other person, and now the question is when you talk to each other, right? So Byzantine is not necessarily the real world scenario. I mean, think of an aircraft. You have multiple computers working there, just in case one computer malfunctions.
So is the situation I'm not doing the task, and I'm telling you to figure out the answer,
So-
and I try to figure out who to believe?
So yes. So the whole point is that each one of us is replicated. Hopefully, if we weren't replicated, then if you get hacked, then the person depending on you doesn't know whether you're right or not.
I'm just saying, like, if I'm doing the calculation as well, and I come to one answer, and then all of you do a calculation, and you come to a different answer, but you all come to the same conclusion of the same answer, I'm still going to conclude, well, everybody else was hacked. I'm the only one that's the one that's right. But
True.
like, if I'm not doing it, if I'm not doing the calculation, then I guess I just take a poll.
You take a poll,
I
right?
don't know what the right answer
So
is.
the model is that you've got a distributed program composed of modules A, B, C, and D, right?
Those modules meaning nodes, right? Or is that?
Yeah, think of them as processes on different computers,
Okay, 'cause
right?
Those modules, I think, it's like libraries, not.
Yeah. Processes on different machines, right? And we know that at any point, and this might be your car. I mean, if you want to think of your car and that'll become more interesting, that you've got your fuel injector, you've got your other components, and any one of those components can fail or be hacked in today's internet world. So if we want to go and make sure that your, I don't know, what does fuel injector give its output to? Some other module, the engine. So, okay, so if we want to make sure that that there's fault tolerance, we're going to replicate each component, right? Hopefully all will not get hacked or fail. So what's going to happen? So I've replicated. Now we're doing multiple calculations. Okay, now we've got, and we're doing replicated calculations because we want fault tolerance. Okay, so now what does the engine believe? Majority, right? So basically what happens, but the engine is replicated too, right? So that means the fuel injector has to go and give its output to each replica of the fuel injector will have to give its output to each replica of the engine, right? That's going to be that's called active replication. Okay, and can you think of passive replication?
Could you repeat what's an active replication? I'm a little confused.
Okay, so again, let's go to the problem. There's module A, there's module B. Module B depends on module A.
Okay.
We know that A can fail at any time. So we have A prime, A double prime, A triple prime. Okay? Somehow these modules have to be kept consistent. Assume that initial condition is that they're all consistent. Now, in the original program, A had to send a message to B. In the new program, what would happen?
In a new program,
With fault tolerance.
all sent to all these A's send to B and B.
All the B's.
Oh,
All the A's will send to all the B's.
you have
This-
multiple B's.
Everything can fail.
Okay.
And then each B will take the majority of the output of all the A's.
Okay.
Okay? So ABC replaced by A, double A, triple A, AI to AJ, whatever, AN, and B replaced by so many B's. And when in the logical program A had to send a message to B, in the physical replicas we'll say that each of the A's will send a message to each of the B's. And each of the B's the receiver will choose the majority result of what it got. Okay? That's assuming this malicious thing that things can just be faulty. What about assuming something more conservative, that it's either working or not working?
And it's simpler. You just get a failure state or you get a message.
But what if a fuel injector fails now? It's not malicious. It's not giving me the wrong reading or telling me to go and put the wrong amount of fuel. It's just stopped working.
Then you just rely on the replica.
Then you rely on the replica. So it's always A is talking to, so there's always a primary guy.
Okay.
We still have physical replicas, but there's a primary guy that's doing the communication, and the secondary guy is just keeping the same state, so that if the A fails, it can take over from there.
Is this only something in like failure model where things just die?
Yeah, that's what I'm saying. This is much simpler one. Yeah. So it's a simpler model.
So
That-
like what happens in the assignment?
So what are you doing in the assignment? Which model?
The passive.
Passive,
Yeah.
right?
You replicate your relayer in the master node
Yeah.
everywhere.
Everywhere
And then you do election, a new master.
takes over.
Yeah.
Right. So your assignment has got a lot of fake things in it, or some fake things in it at least. And the reason I'm going through a more abstract discussion is to show you that there is some specific general idea that you're implementing, and that was my goal when I designed the assignment. Not so much, to show you some larger class of problems that you're dealing to some level. Okay, the most abstract level you're doing fault tolerance, and less abstract you're doing passive replication. Okay. Now let's go and talk about this. We said, we'll just take the majority result. And that's called the consensus problem, that we'll just go and, figure out what the right consensus value is. How easy is that problem? To decide what the majority value is.
I mean, depends on whether you think a majority of plurality or.
Yeah, but let's assume there's an algorithm.
Okay.
Whatever you choose, whatever the algorithm is.
But we're assuming we can reliably verify that this is from this
Yes,
person,
yes, yes,
this
yes.
is from that person.
Yeah, we assume that that's done. Or we can I don't know if we need to do that, but we need to, because we can just choose without knowing from whom a value came.
Well,
We can still choose
if you're, if I'm really malicious, I'm going to send the value to you multiple times.
Yeah, assume it's sent only. Yeah.
Yeah.
So we can validate that we don't get.
But if you send multiple times, you can tag it with the same sequence number.
Yeah. So we assume that happens. Okay. All right. Or what we do then is that if we get, and of course we can do some detection that if we get more than the expected number of values.
Yeah.
But then of course if somebody has died, we don't know.
Local sequence number. too.
Yeah. But how hard is it to do distributed consensus?
You said it was hard.
I believe it's a hard problem, yes.
Why? You just get the messages and whichever, add up the messages somehow using some algorithm and choose the correct value.
this specific model that we're thinking of right now
works. So the consensus problem is that the processes decide on some value. Example, who relays, whether the transaction should be committed, which value to choose. This is a very classic problem. And they talk of two kinds of systems, asynchronous systems and synchronous systems. Asynchronous systems, no bound on the time required to respond to a message. Okay. Synchronous systems bound on the time required to respond to a message.
So synchronous hard, asynchronous
Easy. You know, the more flexible things are, how hard is it?
which one? Asynchronous?
Yeah, because asynchronous is harder than synchronous, right? So how hard is it? Is it impossible? Is it NP complete? Is it quadratic?
It could go on happiness, it's boundless, so it could never end.
So you can never solve
Whenever
it.
you figure out the
Just
answer, you know, the next, like as soon as you do that, the next response could come in, right?
No, we know that there are going to be n responses. You know.
Yeah, but like at some point you have to decide, okay, that one's died.
But the point of this one is there's no bound on our time.
Right, and with failure, we don't know whether
If it is failed or
if it's failed or not. Okay. So if you go and look for talks or papers on distributed fault tolerance, based on my little bit of Googling yesterday, 80% of them will talk about the proof for why the asynchronous consensus problem is impossible. Okay? There's 2 or 3 lemmas that these guys came up with, and it's one of the classic papers. And it's, you know, in many ways it's in the same class as NP completeness and halting problem, that it tells you what you can't do, so you shouldn't even try doing it. Okay? So in synchronous systems the problem is easier, but can you think of some impossibility results even there?
Well, more than half of your processes are in some kind of Byzantine failure mode, then
So intuitively, if you know, the majority is malicious, then you're in trouble, right?
yeah.
But the trouble is that you know, this can propagate, and you know, a lot of this stuff has happened since I graduated. But the Byzantine problem was being done while I was graduating, so I actually remember studying the papers. And they're pretty complicated. But it's the bounds are a little less obvious than what Chad said. So basically, if there are m faulty processes, you need at least 3 plus m plus 1 total processes. Okay, so it's not just majority. And the talk you were going to give, had I not had a talk on Tuesday, was these 2 talks basically. That was what was in Jim's slides. Okay.
I knew it wasn't just half bound, but like that is
Yeah.
one bound.
Yeah, but we can imagine that there's a bound, you know, that. So that's what my main point is. As long as the ratio is above a certain threshold, okay, and we believe that intuitively, and you know, we can get into a proof. And by the way, this is also not just a very obvious solution thing here. There's a very complicated proof here, and very elegant one. Okay. Okay, this is going to be important when we
Do you
design.
remember the proof for the synchronous thing? So I don't remember.
Do I remember the proof?
Yeah.
No, I mean, I don't know. I studied it, in fact, in college, but in grad school, but I don't remember the proof. But they're not too hard. I mean, this one is the one that people find more attractive intellectually, because there was a big debate apparently that can you achieve consensus in asynchronous system or not, and people didn't know till these guys came up with Nancy Lynch and I forget who else, who were the other authors, came up with the proof for this. And actually, I spent some time looking at the proof. So if you ask me to look at the proof here, this proof I did spend some time on. Here, I've seen so many Byzantine papers that they're all a blur, and so I can't, I just don't remember anything from them as a result. So the intuition there is I do not know if a process is faulty or taking too long, and the intuition the other one is that, you know, if If they're malicious, then they can confuse you. And what happens here is that there are rounds of communication with timeouts. This is synchronous, and that's how the algorithm works and tolerates these faults. Okay, so that's general. Now we're going to look at fault tolerance while trying to achieve consistency. Okay, so we're not going to just look at a specific application like our application of the simulation, but generally consistency issue. And then in consistency, and we're going to look at atomic broadcast, not arbitrary consistency, and we're going to look at the fixed sequence. Okay, so we're narrowing down tremendously. And then in the fixed sequence, we're looking at unicast broadcast algorithm. Okay, so further narrowing. And what are we going to use here? We're going to use passive replication. Okay. And the reason we can use passive replication is that because we're doing atomic broadcast. And because we're doing atomic broadcast, we know that all the processes are, can be in the same state. Right? So what do you guys think? We should do synchronous system or asynchronous assumptions? Can we do asynchronous? Why not?
Sounds good. You want to just go over that?
That was consensus problem. Here we are trying to just achieve atomic broadcast.
Oh. I mean, they're not returning anything. There's no implicit need for synchronization.
They're just trying to keep their state constant. So actually consensus problem is that all processes agree on the same final value.
Mm-hmm.
That's a consensus problem as a result of some communication. And here I'm saying the communication is atomic broadcast. We know the consensus is impossible.
We still can do atomic broadcast.
We want to do fault-tolerant atomic broadcast, remember? Atomic broadcast we can do, of course. We know that we can do consensus, but not a fault-tolerant consensus. Because if we know that no process fails, we'll wait till eternity till we get a value. So we know we can't do fault-tolerant consensus. We know we can do atomic broadcast. You guys have been doing that in part 1 or part 2 of your assignment.
Can't you short circuit this consensus process and say if you get enough for consensus, even if process X has failed?
Sorry, say that again?
Assume consensus.
Can we assume consensus?
Yeah, can you get enough for consensus? Can't you get enough information for consensus even if a process has failed?
No, the consensus problem says that you can't, because you don't know whether some communicating party failed or has not returned.
But could you just, I guess, why can't you cross your consensus threshold, even if just assume that they would have given you some bad information and they would not, you wouldn't consider them for the consensus. But you get 7 of your 8 processes back and say, okay, that's good enough for me.
But how long do you wait? And I'm going to hand wave here a little bit.
Yeah, but
because there's a very formal proof here. Okay, and with these answers, the arguments I'm going to give you, that's not going to be a full answer. But the intuitive thing is that how long do you wait? That problem doesn't say that in some situations you can't achieve consensus. It says you cannot achieve consensus in all situations. So true.
So assuming half of your processes are sort of hung indefinitely on the world's slowest.
So the worst case scenario says that you can't achieve consensus. That there exists a schedule or exists a set of initial conditions is what they call, that can lead to and a set of messages that can lead to not having consensus. Okay, but given that, so obviously we've tried to simplify questions, our problem as much as possible. So why am I asking you should we do asynchronous, synchronous? The answer must be that atomic broadcast, fault-tolerant atomic broadcast is impossible if we assume asynchronous system. And can we prove that from the consensus problem? The consensus problem is that n processes all decide on the same value in the presence of one or more faults.
But here, like, when you're, like, what are all the things that are involved in atomic process, on atomic broadcast? Does it, like, all of the values eventually get there,
Yes.
but it doesn't also imply time frame, right?
So,
Because if you're just saying broadcast and it doesn't necessarily have a time limit, then you could be able to do atomic broadcast without that meaning that you
okay, so
could-
atomic broadcast means that each process receives the same set of messages in the same sequence. Right?
Okay.
And if I can guarantee you that there will be eventual atomic broadcast,
Mhm.
fault tolerant broadcast, that's what you have to guarantee.
But can you really use that to build a
Consensus problem?
consensus?
Because if they've all received the same set of messages, same in sequence of messages, they'll all go to the same state.
Well, eventually,
And that's what the consensus problem also says, eventually.
but at some point, it's got to make a decision on that message is never coming, and that process that sent that has died.
Right, right.
And then after it makes the decision to do that, and then go on to its next.
Yeah, so consensus problem is a very simple problem. It says that we're just going to decide on one value.
Mhm.
And that's it. And we're going to guarantee that we all achieve consensus, that every one of us will agree with the same value. And atomic broadcast, reliable says, if we can achieve atomic broadcast, then we can achieve consensus. So atomic broadcast is a harder problem.
But like, so when you say in the same order, is that in the same order that?
All processes will receive messages in the same order.
They'll receive my messages
No, no,
in the same order, or the same message from
Set of
everyone?
from everyone. That's all.
Okay.
That's all. Right. So asynchronous systems, if we can do fault tolerant atomic broadcast, then we could have consensus, which is impossible. And by the way, the other way around is also true. That if you can achieve consensus, you can achieve atomic broadcast. So that this is again like NP-hard problems, that NP-hard problems reduce to each other. So this is why these impossibility results are interesting. So that's why we will, and we can. Remember when we were talking of the algorithms, various algorithms for achieving atomic broadcast, we were talking of whether to put bounds on the amount of time it takes for a message to arrive or not. And we know now that if we don't put bounds, that's what I kind of hinted to you at that time, then it's just impossible to achieve atomic broadcast. Okay. So the interesting part from implementation point of view becomes synchronous systems. Okay. And I tried to look for some papers on atomic broadcast and synchronous systems, and they were talking about okay, do we assume reliable communication or unreliable communication? Do we assume application level or network level broadcast? Okay. So for instance, Amoeba, have you guys heard of the Amoeba distributed system? It was in the 80s. You know Tannenbaum, right? He's written network books on network protocols. Nobody, not even you, fan. Okay, guys, your mobile computers need to be far away.
I just keep playing the case.
Okay. So I saw an algorithm. I said Tannenbaum invented Amoeba. So we have reliable. So what we're going to assume is reliable communication. We assume that we got TCP/IP. Okay, and we're going to assume application level broadcast. So we don't. So it's point to point, and it's not some network level broadcast. Okay, so there's some algorithms that go and take other dimensions. Okay. So I couldn't find any paper that addresses these constraints. As far as I could. I didn't look that much. So what's the basic idea? We just assume that each message has been sent to each of the current session members. There's no latecomer, right? And assume synchronous system. Okay, we're going to assume what Chad mentioned, that there are probe messages being sent from each side to the sites to which it's connected. And if a probe message doesn't come within a certain threshold or time, we're going to assume that that machine is dead. And if a message does come later, we're just going to throw it away and say, sorry, we don't consider you alive any longer.
A message from that particular person.
I mean, it's possible, right, that you send me a message which has gone through Hong Kong, and then I send you a message directly saying, are you alive? And so that message doesn't come back within 2 seconds, okay? And your message comes later after 10 seconds. We're just going to discard that. I assume that's how TCP/IP works, okay? That's kind of what you hinted. And I know some other protocols I've studied that do exactly that. Okay?
I mean, mechanically, if you've gotten the exception already and
Yeah.
then you've gotten rid of it, like there's no way.
No, I meant the probe messages. I assume the probe messages are being sent periodically.
But
And that's how you will have to know.
I thought you were meaning like if one of the probe messages fails.
No,
Right.
no. What I was saying, the second part, you're absolutely right. That if a message arrives after the probe message has failed, it has to be discarded. The
Yeah.
connection is no longer alive, right? We'll assume that we don't have to solve the consensus problem to choose the next relayer. Okay, we'll assume that each site can run a local algorithm that decides on the next relayer, and somehow we have the IDs to resolve that. Okay. Assume no erroneous or malicious code or hardware. Okay. And we'll also assume peer-to-peer, that there's a special relayer site, that any site can act as a relayer. Right? So that's what we're doing. So what do we need? Okay, so we're going to look at not just the algorithm, okay, because like I said, with these constraints, I can't find any paper that thinks this is worthwhile talking about in an intellectual way, right? So maybe all that we're achieving here is learning how to do something more general, like passive replication, right? But I do want to go and address the architecture part. So we do know that there's a relayer object and a client object and a session port. And what are some other objects we need in this situation?
Policy manager.
Sorry? No. So right now, let's assume no fault tolerance, but peer-to-peer architecture where there's no specialized relayer server.
Session server. But, no.
Yeah. So session server is outside. Yeah. That's part of session port here. Remember, it's peer-to-peer. There's no distinguished site.
Election.
You need an election manager, right? And we also need to know when somebody leaves and joins.
Connection is.
Okay, good. See, this is what you get from implementing. It's in your cache. Okay, so we'll start with this architecture, and before we go further, so client object can be and the client object can be composed of model in and out coupler. I didn't mean to show you this part, so we're going to talk about connections now. So what is the awareness in these objects of each other here? So I've got 5 objects here. Session port, who all are aware of the session port?
Client object, connection manager.
And relayer object? Relayer has to send a message back, right?
Yeah, but it doesn't have to. I thought you just registered the object with the session port, and then use the object like you would normally. The object itself doesn't know about the session port.
Yeah, so I haven't quite gotten into RPC versus non-RPC. And sure, things are hidden for you in RPC. But when you're doing message passing, the relayer object has to go and send the message to some port.
Yeah. I'm still just thinking of things like Gypsy where you're trying to take that extract from.
Yeah, so in Gypsy, the relayer object uses some proxy that it got from to send it back. And yes, that's kind of hidden, but it's there that the proxy it uses a proxy to talk back to the client object.
So the client relayer is aware of the session port.
And
Once you because you, yeah.
Also connection manager, right? Like you said,
Yeah.
right?
Yeah, right.
Okay, so what about the other relay elector? What is it? Is it you know?
Elector knows the clients and
Connection manager.
connection manager knows the relayer.
Connection manager knows the relayer,
The electors.
elector, right? And the client object,
No.
how does it send a message to a particular relayer?
It asks the client manager for the proxy. At least that's how I have
It asks whom?
the connection manager for the
Okay,
proxy.
so it has to be aware of either the connection manager or the relayer, right?
Yeah.
Okay. So connection manager is aware of the is aware of the relay elector, and the client object can be aware of the connection manager, right? Which is exactly what Jeremy is. Okay, what are the various events in the system now?
Joining,
Joining, leaving,
Leaving. Sending message.
sending what message?
sending a message to the relayer,
Broadcast.
broadcasting, and
Sending the broadcast request.
yeah,
And broadcast the message from the relayer to client.
Sending the relay back message back.
Yeah.
And then with each send there's a receive also. Event. Right? So send broadcast, received broadcast, sent relay, received relay. Right? Left, joined. Okay, I should say member join. Okay. So here's the basic algorithm, simplest algorithm. So we again, you know, when a fault occurs, let's start with the straw man. So when the leaving of a relayer is detected, the next broadcast is sent to the new relayer. Okay? In server algorithm, when the leaving of a relayer is detected, the client object is removed from the list of clients. Right? We have to do these two steps. And can these steps be sufficient under some conditions?
If there's if the error is not happening in the middle of the broadcasting.
So there's no partial broadcast. Right? So, we're just going to go a little incrementally to our final algorithm. Okay? Now I use the passive voice. Word will scream at me, and this is bad English according to American way of writing. But I first used the active voice and then I used the passive voice because the question is, who does this? So which object is make sure that this is what happens. How do we change our architecture and how do we change the functionality of the various components? And we've got the components on the right.
well, the connection manager is the thing that detects when
this.
the relayer is leaving.
Okay, so it detects the leaving and joining.
Yeah.
And then the client algorithm just automatically so
So the elector runs the election.
so the connection manager runs the election again,
Yeah.
right? And in that server end, how's the list of clients removed?
So it can be done past late
So
evaluation way. Like
with the server algorithm, you mean when the client object is leaving a client object is detected?
So the current relayer,
So like the server algorithm is the relayer algorithm, the relayer's algorithm, right?
right. So did I get a little confused here?
Leaving a-
So now there's going to be a new relayer, right?
Yeah.
The new relayer has to not send.
To that, yeah. So So, yeah, so.
So how did you guys do it?
I'm on as the list of clients in my connection manager, and when that client gets disconnected, we check to see is that client the current relayer. If it is, I have a current relayer set to null, and then remove that from the list of clients
So the list of clients is kept by the relayer, right?
by the connection manager, and then the relayer asks the connection manager for a list of clients.
Okay, maybe that's the way to do it. Okay, so the
I maintain the list and the relayer in the elector. So every time you send something, you have to ask the connection manager about the destination of this message. So at that
okay, no, that I understand. The client asks the connection manager
for the
next for the current relayer.
yeah.
What about the relayer? How does it know which set of clients to send it back to? To send the messages to. Your relayer itself must have a leave and join somewhere, right? So how does the current, each relayer has a list of clients to which
Yes.
it sends messages. The client's objects do a join of the relayer and do a leave of the relayer also, right?
So the relayer knows. In my implementation, the relayer is just a special
Object.
client. I mean, so it's also aware of the connection manager. So it asks the connection manager for the client's list.
Okay.
That's what I did too.
Yeah, I think that's it.
Okay. Okay.
Because I think it is the elector knows everything. Knows the current state of the
See,
system.
the way I have my elector is it's just a object that sorts the clients.
Yeah, me too.
Yeah.
I just
So in your old RMI implementation, your relayer object had a join and leave call, I assume, right, of some kind. When a client joined it,
yeah.
in your RMI and Gypsy,
Yeah, to subscribe. Yeah.
yeah. So
Yeah.
I kept the same object, and then the connection manager has to go and call join and leave, or somebody has to call that leave method.
Yeah.
Okay, but if you just design and if you're going to change the client object to go through the connection manager, why not also make the relayer object go through the connection manager? So that's fine what you guys are doing. Okay. Assumption relay does not die in the middle of sending messages. Passive voice. So we'll just have now, we won't do it in the connection manager so much as that we'll now have a master and slave fault tolerant manager. And they'll go and make the changes for us. Okay. And again, I'm glad you thought that separating the manager into slave and I didn't do it, but I wished I had done it after I'd done it. But since I had not actually changed it to slave and master, I didn't want to go and force you guys to do it because I didn't know the pitfalls that might arise with that architecture. I knew I was able to overcome the pitfalls.
Yes,
Yeah. So, okay. So what you guys are doing in your connection manager, is somewhat done by the FT manager here. Okay. So let's now go and address the problem of the relayer not dying in the middle of. What happens if you have partial broadcast? So what was the solutions that we looked at?
So if it dies in the middle, all the clients detect the error and send the most recent message to the new relayer
Okay.
to figure out which is the latest one.
So whenever a client dies, so whenever a member dies, then the client messages go and send their most recent messages to the. Okay.
And the new relayer figure out.
What if the relayer, so we want to assume atomic broadcast, and we want to assume that all the remaining processes go to the same state after the fault tolerance. What if the relayer site had generated a message, send that message to one site and not others?
My implementation is just send the message to all of them and let the client figure out. If the sequence number is smaller than the current one, you just discard that message.
No. That's fine. You told me that your solution was, which is what I suggested in my assignment, that each client keeps track of the latest message it has sent
Yeah.
and sends that message to the new relayer.
Yes.
Okay, so that works.
But we need to send more than just the most recent.
Okay, but that's your algorithm, right? That your algorithm, but I'm
Is
trying.
anybody not doing that?
But
No,
it
no.
depends,
There's a
on, depends on how much you
new
buffer.
member.
Sorry.
I mean, there's a new client to join in this.
Yeah, but even in that case, we could have one message get lost going to a client where normally TCP would like take care of that and resend it until it arrived. But if it failed and it hadn't sent a second message, then or the broadcaster had started sending out a second message, then something could be 2 messages behind, not just one.
Oh, okay.
No. Okay, so
Simon assumes that only one.
yeah, no, because you remember, this is the algorithm I came up with, and Chad was finding holes. I want to remember what the holes they were, Chad, because we are assuming reliable communication, we are assuming TCP/IP, we are assuming timeouts, right? So, but before I go to Chad's situation, okay, let me point out the following issue, which is a simpler issue. So, I was a relayer, right? He sent a message to me, and I die, right? Now he'll send the message to you, the new relayer. That's fine. What if I had generated a message, send the message to him, and then I die, and you're the new relayer? That message, he's got that message, he's processed it. We want to make sure all.
You send to him he's a relayer.
No, I was the relayer first.
Okay.
You're the new relayer.
Broadcast the message to him.
Yes,
And you die.
I die.
And then
You're now the new relayer.
okay.
He's going to send you his last message, right?
Yes.
His last message is the last message he received, the last message he sent.
But he received the last message he sent.
Which message will you send?
Wait, I
So let's do this more formally here. Okay, passive replication requirements. Any message sent by a remote client to the dead relayer should be received by all clients. Right? Eventually.
yes.
Any message sent by the dead relayer to a remote client should be received by all clients. Okay, so we have to have these two conditions. Okay. So one or more clients has the messages that the old relay partially broadcasts, which can be rebroadcast using the old relayer. Using the new relayer, sorry. This should be new. That's the key idea, right? And we can come up with some variations on how long the history to keep and what the consequences of that could be. Okay? That means the sent messages must be buffered, right? Somewhere. And received messages should also be buffered. Okay, so that's the higher level thing I'm coming at. Right? If we buffer all messages, we achieve both goals.
Then that's for the attaching the last scene, the latest seed, at least seed sequence number with the message, because then you know how many buffers.
Exactly. Okay, so changes to basic algorithm. When a leaving a relay is detected, synchronization phase is entered. Okay, so now we have to go and enter a synchronization phase. Okay, when messages are rebroadcast. Okay, so again, in both these algorithms, that has to happen. And we have to wrap message with current sequence number before it is sent to the client object. Okay, so that the client objects know what they received. Okay, and the sequence numbers are used to determine what is rebroadcast. Right? So at a general level, that's what the sequence number is doing. Right? So both the client and the server get into the synchronization phase before doing new relay. So architectural changes. What new objects do we need here now?
Masters.
You have to attach sequence numbers.
Sequencer.
So how are we going to attach sequence numbers?
Uh,
Wrappers and yeah. And what are these objects going to be? I mean, they're going to be the filters in Gypsy, right? Okay, and then during synchronization phase, new messages are buffered, and at the end of the phase, they're sent. Okay, so we have synchronization phase, we have sequence numbers, and the client algorithm uses the sequence numbers to determine what is rebroadcast. And while this phase is being entered, new messages may be generated, so they have to be buffered. So that's to make sure that the synchronization phase ends. Okay, so that's another complication. And again, in both, and this is common to all algorithms that we've come up with together. Okay, so now you need a filter objects also, send and receive filters. And who needs to be aware of the filters, and how does the filter object, what is the awareness in the various, among, who's aware of the filter and what is the filter aware of?
I think we need to add the chapter to this architecture because
Add what?
Chapter, the message chapter.
Chopper.
Chapter.
That's a filter.
Okay.
Sorry, I should have called that trapper.
Okay.
That's my filter object.
Okay.
Yeah, the trapper object. Yeah. So who's aware of the trappers, and what is the trapper aware of?
So both it.
It's the manager.
Sorry,
It's aware of the manager.
the fault tolerant manager, and also the fault tolerant manager is aware of it,
Yeah.
because the fault tolerant manager sends messages through it,
Yeah.
and it sends messages to the fault tolerant manager.
Yes.
Right? So you've got these filters. The filter is, obviously sending, it's got some awareness of the session port because it needs to know what the next stage in the pipeline is. And the filter is aware of the fault tolerant manager and vice versa. Okay? And we want to keep the filter logic to be as little as possible because it's aware of Gypsy.
Yeah.
We want our algorithm to be mostly Gypsy independent.
Yeah, the way that I have mine set up right now is to just grab something and pass it to the...
Passes it, right? That's great. Guys, we're going to take a little bit more time than this. I just got, I think, 9 slides left. But, and can be separated into master and slave FT manager, right? So now we have, in addition to the previous events, send finish synchronization message, right? And receive finish synchronization message. And the synchronization, so did you guys have that? Do you have that also?
I haven't gotten there yet.
Okay. That is sent by the master to the slaves.
Yeah, so how
Do
do
we?
you... Go ahead, you first.
But what do we need to send the start of the
Synchronization?
message?
What do you think?
Because if the relayer leaves, everybody knows.
Everybody knows.
So you don't need to.
You don't need a start synchronization,
Yeah.
right?
Yeah.
Oh, sorry.
And
I read it wrong.
we agree, when we talked about this, was just in case there was some, some delay in someone realizing that the replayer had died.
Yeah. So that is the reason why I think it was very important to go and get a model right. We've got our timeouts.
Yeah.
We know within that timeout that things will happen.
Yeah.
So things were getting a little confusing when we were doing the other algorithms. Okay.
Yeah. And how do you use your manager to send a message? It's like I understand when you're sending a message, you grab it and wrap it, send it, unwrap it,
Yeah.
understand it.
Yeah.
But when there's no you know.
When you generate messages?
How do I generate a message to be sent?
How do I generate a synchronization message, for instance, finish synchronization message?
Yeah, and how do I send that without
Right.
attaching it to an already the message that was going to be sent?
Okay.
Like, do we register another remote object, or do we?
So have you tried to see what the filter object gets actually when you make a method call? So you make a method call, and so how do you attach messages?
So you will get a serializable call.
So you get a message. Your RPC call gets converted. In fact, in my implementation, the proxy call gets converted into a call all, which Chad was mentioning. There's actually, through reflection, it does a call all, and the call all then gets converted into a message, which is a serializable message. So as far as the filter is concerned, it's just sending messages. And if you want to invoke method calls at the other end, you know what the method call format is like because you received a previous message like that. So you either copy it, you wrap it, and so you just send an object. In fact, your trapper is calling your serializer.
Yeah.
So it's just giving it a serialized object, and your serializer will go and convert it into a byte buffer. The byte buffer gets converted. So the RPC call gets converted into a serializable call message, which gets converted into a byte buffer.
So I understand from when you have a receiver gets a message and then sends it and it starts through that pipeline.
So when it sends a message,
it sees that. But so you're saying the trapper, the first time that it sees this message going through, it copies that procedure call so that it can then call it itself.
it gives it to the FT manager. The FT manager will go in.
So the FT manager keeps a copy of the...
Or keeps the same message if it wants and just sends it later. Yeah.
Okay.
And it can send in any other message. It can send foo, bar, anything it wants to.
Yeah.
So the synchronization message is going to be a special message which doesn't correspond to any call.
Yeah.
Okay, so it will be a special type.
It is special.
Yeah, I make it as remote call in a
Oh, you faked a serializable call there?
I mean, because I have a coupler and I registered the master and the slave for Tolerant manager.
Mm-hmm.
So I can have my master call the end sync method to remotely on the slaves.
But if you do that, you go through the whole pipeline all over again.
Yeah. So that's why I have the complexity there. So
That's why you were getting into some problems or deadlock also perhaps.
No. I didn't get into the deadlocks, but when I have my master and slave together, I cannot tell who sent this message, who sent this synchronization message. So
But I don't think you gain anything from because you just need to send a bit saying end synchronization. So just inject a message type.
Yeah, maybe that's a proper way to do.
That's what you should
Yeah.
do. Okay. So must somehow generate application-specific sent broadcasts and sent relay messages and distinguish them from synchronization messages. So this is important because your trappers have to go and pass some messages through and not other messages, right? And you had to, there are messages being sent to the session manager, for instance, and those don't have to be intercepted by the fault-tolerant manager. So your filter objects needs to distinguish between messages that are internally communicated by Gypsy and those generated by client and relay object. And so what we can do is we can have it aware of the headers of the messages that the client, that are application-specific messages. These are the messages that have to be intercepted. It has to know which messages to intercept and which not to intercept. That's a basic logic. So it needs some application-specific knowledge. And we can encapsulate that, and the way I did it was it had a list of headers. And if it was this header, it said, okay, I'll go and give it to the fault-tolerant manager. Otherwise, I'll let the call go straight through. Okay? And that's what's happening. So assume the client and relay objects make remote procedure calls. The message passed to filter objects are instances of serializable call. This should be passed. The two-header method of such a call tells a signature which can be specified in a list.
I didn't find this method actually.
It's there.
Where is it?
In a serializable call?
No.
Yeah.
No, definitely not.
I use it. Maybe I spelled it wrong here, but there's a two-header method.
I look at the class and I didn't find anything similar, any method similar to this. Maybe
Okay.
I have an older version of it.
No, you imported the new version with a new example.
Yeah. But I didn't find this method actually.
Let me know if anybody else has that problem. There may be maybe I didn't. I'm sure I pushed it.
Okay.
So how did you go and distinguish?
I created my own message and add headers to it. So yeah, it's really.
No, but you still have to go and know which signatures are Gypsy calls. For instance, Gypsy makes calls to session manager.
What I did is I wrapped it with my own object and passed my own object to the remote, and remote just unwrap my.
So, in the serializable call, you look for a particular object.
Yeah.
Okay. Yeah. No. This is much simpler.
Yeah.
Okay. It's a string. The two-header method will return string. Okay. So here's another problem. We said that the relayer has to go and wrap the messages it sends to clients with a sequence number, right? Now what's really happening? The filter object gets the message. It sends it to the fault tolerant manager. So the fault tolerant manager assigns the sequence number. And then the message goes to the relayer, which goes and echoes back the individual messages, right? And those individual replies have to be wrapped. So how did you do that?
You mean the add back every message?
How do I go and put a sequence? How do I attach a sequence number?
I have a method called ack in the client. So not in the client side, in the slaves. So the master just called the ack method and send the sequence number back.
Oh, in a separate message.
Yeah.
Okay, no, but you don't have to do that. You should ideally just go and wrap the serializable call in a message with a sequence number.
Yeah, you could add just a simple delimiter of a string to the end of the command that you're gonna broadcast, and then when you go into the trapper next, then you can find that.
Yeah. I would just wrap that message in another object, and unwrap the object from the other end.
But I'm saying the relayer's broadcast method that's going to be sending out to it expects a string of the command.
Yeah.
So when I go through the fault tolerance manager, I get a sequence number. Now this string is associated with that sequence number. But then I pass that string to the relayer.
Yeah.
Who then calls the broadcast on that string, and then it gets trapped, right? After it's.
Oh, so you're assuming that. Interesting. So you know the syntax of the broadcast call.
Yeah.
You're assuming that the fault tolerant manager knows that it's a string that's being sent.
Well, yeah, because it has to pass the thing that it got to the relayer, so it knows it has to be a string.
It could be anything. Could be an object. Could be a file. Could be a bitmap.
Yeah. So but it still passes. So then, not a string, object. Pass the object to the relayer, who then sends that object off, and that object gets caught in the pipeline.
Okay, but what if the relayer takes 7 arguments? I mean, maybe that's, okay, so that's, you're just saying what if it's not an object? What if the relayer is expecting a string, okay? Or an int? What if it's expecting an int? What do you do in that case?
It's expecting an int. then this int gets a sequence number from the fault tolerance manager.
But how does the int now capture the value to be broadcast and the sequence number? What you're saying is that you just, and that might be a clean solution in many ways, because what I've got is dirty in its own way. What you're saying is that the relayer is given the sequence number.
Yeah. And then
But what if the relayer is not expecting the sequence, an object that?
Because you're gonna grab it on the way
I know,
and then
but the
process
relayer
it.
object is a method, right? The method takes parameters of a certain type.
Yeah.
What if that parameter is just an int or a boolean? How do you give it a?
You encode that extra information.
Yeah, how do you encode that as a boolean? How do you encode your sequence number as a boolean now? Okay, so that's a problem.
Yeah.
Okay, and I'm not saying you change your implementation, but at least I want you to understand, what the limitations are.
I mean, I think it's always hard when in these kind of situations where you're thinking we're trying to be general, but when you're thinking about our specific case, then there's
Yeah, sure.
ways around it.
So again, I'm trying to give you the general algorithm
Yeah.
that the filter is involved in giving the message to the guy. The filter is involved in getting the response back.
Yeah.
It knows that there are n responses that are going to come back. So those n responses, it can put the same sequence number back.
Wait, say that again.
So you are the relayer. You go and broadcast only booleans.
Okay.
I give you the message, right? Because it goes through me. I'm the filter object, and the filter object gives to the fault tolerant manager.
Yeah.
So I give you just the boolean. I know you will go and return me back 5 messages in response, because you're a relayer, and there are 5 guys to whom you have to broadcast.
So you're saying that will lead to 5 sent messages that get sent.
And those 5 messages I'll wrap with the sequence number.
Then how do you know those that one should? It's just that you give a sequence number to sent messages come out.
Yeah. So
Okay, I see.
So when for each broadcast I receive, I assign a sequence number, and then when I get the echo back, I go and wrap that sequence number in it. So that logic is far more complicated,
Yeah.
and that makes it more independent of the exact relay.
Okay.
Okay. So please understand the algorithm if you haven't implemented it, because
Yeah, no, I see what you're saying.
Okay.
Too late.
Oh, you start over.
There's an exam still coming up. When you guys asked me, when my thesis was about to, was in jeopardy of what was more important, the code or the thesis. When I wrote my thesis, I said, assume the code was this.
Yeah.
This is my design. I'm not giving you the design I actually implemented, but I've learned enough from it that I can argue about the design I really want. Just server FT manager keeps track of n, the number of clients, and
Is that what we do in our reports?
no, the video. What are you going to do?
Assume the video showed.
Well, anyway, the famous joke about the fire. The fire, a mathematician, physicist, engineer.
Maybe.
So there's a fire, and there's a mathematician, a physicist, and an engineer sleeping in the room. So the first time there's a fire, the engineer sees there's a bucket, and so he just fills up the water completely and douses the fire. Goes back to sleep, another fire. This time the physicist wakes up. He figures out, how much heat there is in the fire, figures out how much water he needs exactly, measures that water, and douses the fire. Third time the mathematician wakes up. He sees the fire, he sees the bucket, he sees the water, he says, oh, solution exists, and goes back to sleep. So, okay. Here's a concurrency issue. During synchronization phase, new messages are buffered, and the end of the phase they are sent. So assume that we are at the end of the phase. How do we, while we are sending the buffered messages, new messages may come about. So how did you solve that problem? Or how would you solve the problem?
Your manager, instead of passing them on, just would collect all of the new messages.
Yeah, so the new messages are in a buffer, right? That is reading. It's reading the buffer to send the messages across.
Yeah.
But the buffer is, is being populated at the same time.
Yeah.
So, where do we, if you're writing a loop in Java, you'll get a concurrent modification problem. In fact, that's probably what you got.
There will be multiple clients to send the.
While you're sending messages from the buffer, it's being added to. That can happen. Right? You've ended your synchronization phase,
Yeah.
so you need a synchronized method.
Yeah.
You need to block the other guy. You need to block your client. Your clients will have to block at some point. They're not blocking before that. Before that, they're just sending messages, but now they'll block on a bound. So again, a bounded buffer. This is the classic bounded buffer situation. It's not quite bounded. It's not quite that the buffer is full. It's just that the buffer is now being frozen at this point. Okay. So I don't know how you did your demo, your video, but in the demo I showed you, I had a loop that was just moving the simulation back and forth, and in the loop I'd killed the process, the relayer, and the loop just continued without hiccups in the other clients.
I manually demoed it.
But you should do the loop just to convince me, you know. That's a real test.
Where's the loop?
So remember, you have a loop anyway to go and measure the performance of Gypsy.
That one.
So I killed the process in the middle of the loop.
I just added delay to.
Yeah. No, that you have to do to show the demo gradually, to show all the. But to really convince yourself it works, which is what I did.
Okay.
So I killed 2 or 3 processes in that loop just to convince myself that there's no problem of this kind. Okay. The synchronized methods can be broadcast. Let's talk about the threads now. This is important. What threads are executing all these, processing all these events? Sent broadcast. Which thread is doing this?
The client's receiver.
No, this is sent broadcast. Consider your Gypsy. Assume I'm running that Gypsy. I'm doing that loop, or I'm pressing a button to say move,
Then the AWG thread.
or some main thread or some application thread.
Yeah, but then, yeah.
Okay, so that's good. Receive broadcast. Which thread executes that? Yeah, but the relayer gets a message, right?
Yeah.
So there's an RPC call.
Yeah. And I have mine that just puts that on a queue, and then,
Okay, so you make your own thread.
well, yeah, the broadcaster to send messages, to relay messages, there's a separate thread.
Okay, but which thread actually called receive broadcast?
Uh,
That's the RPC thread.
yeah.
Okay, so there's an RPC thread.
Yeah.
This is that thread. Sent relay. Now in your case, it's your thread.
Yeah.
But in most places, it'll be the same thread that did the receive broadcast.
Yeah. When I changed that, because I had been getting really, really bad performance in the previous one.
Okay.
But when I added that change, it was
Faster?
way faster,
Why?
an order of magnitude faster.
You must have something else going on, because it should make a difference, because this is just RPC thread or your thread. What difference does it make? In fact, threads will cause delays. Okay.
I don't know.
Someday when you have time, you'll go and figure out what the exact, as a true distributed systems person. Receive relay. What thread is it going to be?
Another RPC thread.
RPC thread. Send finished synchronization message.
RPC thread. Or no.
Yeah. RPC thread, yeah. Or actually, no, actually.
Nobody, or it's the
In his case, it'll be,
listener.
yeah.
Connection listener.
In his case, it'll be the RPC thread because he's doing RPC calls. But in your case, it'll be a selection thread.
It's a separate thread.
That's a selector. That's your NIO selector.
Yeah. No more threads. Yeah.
And that is the one you don't want to block, otherwise you're going to get deadlocks. And receive synchronization message is going to be the same thread. Okay? So application thread, RPC thread, RPC thread, RPC thread, select thread. Okay? Unless you go and introduce your own threads, in which case it'll be different. Okay, so, and I'm saying original transmission and retransmission can occur in different threads. So when a message is being retransmitted and sending the broadcast, which thread is doing that?
In my case, it's an RPC, but
No.
no.
When do you do the retransmission? When you detect a client has left.
Uh, uh, select.
Select thread.
Uh,
Okay, so you have to, you'll have to worry retransmission in select thread.
Yes, because in this case you assume that, I mean in most cases you use the select thread to do all the synchronization, but I use the message call, the RPC call. So
No, but it's still
it's more like the select starts the RPC call and.
No. Select call cannot. How do you even make the select call make an RPC? RPC is you have to go to a remote site to get the RPC done.
Yeah, I mean.
There's no way you can get hold of my RPC thread. I mean, that's just too much complex. I understand that your client can go and invoke an RPC call on the other end. Okay, but this is going to be done in the select
I
thread.
feel like my code is too much hack.
No, but you couldn't have done it. It is a select thread. Trust me.
Yes.
Retransmission hackers when a client when a client
Yeah,
leaves.
I think I.
Even if you make an RPC call, it's made in the select thread.
Yeah.
Okay, and just make sure that your RPC calls are not returning values. Okay, now we come to Chad's issue. So sent received messages are buffered and the sequence numbers of received messages used to determine what is rebroadcast. And guys, we've had a long lecture here, haven't we? Now, so the algorithm that we can have is replicated buffering, which is that a client buffers all received messages and unbuffers messages it knows have been seen by, sorry, this text is not complete, that it knows have been seen by others, right? This is what we talked about. Oh, actually, yeah, this line got split. Here's the thing. Unbuffers message it knows have been received by all sites, right? That's sort of what we agreed on. The basic principle was that we'll buffer all messages, and that was Chad's scheme, and we modified it and said we'll unbuffer when we know that other sites have received them, right? And we just send the last sequence number with every broadcast, and we periodically send special synchronization messages with the sequence number of what we've got, right? So remember that whenever we send a message, we say this is the last sequence number I've received, so you guys can clean up your buffers. And if I've been sitting and not sending any messages, every n seconds I go and every n messages I go and send a special message saying please clean up your buffers. Okay, so that's what Chad's going to implement. None of you guys implemented that.
That
And
would just have the special message, not bother.
sure. That covers it.
everything.
That covers it. And distributed buffering, which I don't know if you've done it quite right or not. A client buffers message it has sent, and at most one message from the current relay. Right? Do you get that?
Yeah.
And when do you unbuffer your sent messages? When do you in this
When you receive it.
Yeah.
Yeah.
When you get your echo.
when you receive an echo,
From the relay.
you unbuffer the previous messages,
Yes.
And your sent message.
not that message, because you may have to send it back again.
Oh, so then, yeah, you just, next time you send, you would, yeah, okay.
I'm timing
sure I follow
mine.
what you're saying.
Yeah.
What do you mean? Can you say that again?
So we are doing the distributed buffering algorithm, okay, where we are buffering only our messages, okay,
Okay.
and we are buffering.
So this is completely different out there.
It's a different algorithm,
Okay.
okay, and we are buffering the messages from the current relay, one message from the current relay,
Okay.
okay, and the question, and that is just one variable, so we don't have to worry about unbuffering it. The question is, when do we clean up our buffers? And the naive answer, the straightforward answer is that, whenever we receive an echo back, we unbuffer that message. But that message may have to be resent. So what we do is we go and unbuffer all messages before that. Okay, and now you have to tell us, so assuming that we can be off only by one message.
Okay.
This will work. Okay? And the question is, when will we be off by more than one message? If the relayer had sent 2 messages, you're saying?
Yeah, I mean, like,
If someone hasn't received the message of the relayer, but somebody else has received 2, and the relayer dies.
Okay, so whoever has received 2 will send his most recent message.
But then he needs the most recent 2 messages, because he's 2 messages behind. I'm saying one person hasn't received any messages, and then the other person has received 2 messages, and then the relayer dies.
Ah, right. That's what we were considering. That the new relayer is off by more than one message.
Yeah. But we're also assuming that these issues are caused by network latency issues.
So the current relayer could potentially have a little delay in it, saying, I'll wait for whatever the probe time is.
Yeah.
And by then I know I would have received.
wait, what?
Right, will that work?
What are you saying?
Supposing we know that messages are received within a certain threshold time period.
Okay, yeah.
Can that problem be solved still? I'm not so sure. I mean,
Well, if you knew it was received within a certain time period, then I think you could.
do we know how many messages to wait in that case? Because you can be off by at most
Arbitrarily.
if there are n clients. If there are n clients, the relayer message to you will be received within n multiplied by t time.
You're saying if we have a bound
Yes.
for the amount of time it takes for a message to get to you. Where are you getting this formula?
Because the relayer died in the middle of sending messages, right?
Yeah.
And the relayer went and sent messages to. So what we are saying is that we are behind an arbitrary amount. You're saying we can be behind an arbitrary amount?
Well, if you don't have a bound. Okay.
No, we have a bound.
Okay.
So the question is, the other guys have got messages. Okay.
Then I still think you could be behind by an arbitrary amount. The other connections could just be really fast.
Really fast.
And then, they could have been doing tons of work while you were still.
Right. So I get back from a relayer a message. So what happens? Some guys got the latest message, right? So I go and figure out what the current sequence number is, what my sequence number is. I know how much to wait.
Who is you?
The new
I
relayer,
go and find
the new
out.
relayer, the new relayer.
Yeah.
Yeah.
The new relayer finds out what the most recent sequence number, and then what does he do with that?
The new relayer, the point is that the new relayer already knows. The new relayer knows that the old relayer died, right?
Yeah.
So any messages that come from, so any messages from the old relayer will not reach the new relayer now. Right? After any messages in transit will never be
Sure,
received.
yeah.
And what we are saying here is that there are messages that other guys have received
Yeah.
that I don't have.
Sure.
So wouldn't it be the case that, okay, so you're saying, I mean, intuitively you should be able to put a bound, right? I mean, that you agree with me, since there's,
Well, you wouldn't be able to put a bound on the number of messages to buffer. You could put a bound on how much time you have to keep up messages
yeah,
in your buffer.
yeah, you're right.
I'm pretty sure you could have a timeout for the buffered messages.
Okay.
Not numbered.
So that was the issue, that if you send a bunch of messages quickly,
Yeah.
you can be behind by that, right? Okay. But, so what I told these guys in the handout was that you can implement this algorithm, but you're right. Otherwise, we do need the replicated buffering algorithm, okay? So distributed buffering is that we go in, okay?
So for this, we can just assume that.
Yeah, so I wrote down here efficient but less flexible. I'd forgotten the argument for it. And I thought the argument had to do with how many faults occur during synchronization phase. And I think you convinced us that your algorithm could also take multiple faults.
Yeah.
But I know in the design of my algorithm, I tested it out and I designed it for one fault. But yeah. But I think what we can modify the algorithm by is you unbuffer messages that, you can use a timeout to unbuffer messages too. Okay? Rather than sending a special synchronization message, you can just unbuffer
Over time, so.
over time. Okay? Okay. So when you're doing distributed buffering, we need to know whether our message was came back or not. And how did you figure out whether the message was echoed back or not?
I said I have the remote act. I have the relay act back to every time the client send a message.
Or you get it, you send a special ACK back.
Yeah.
Oh yeah, no, right. But how do you know it's an ACK to your message? Which message is it an ACK to?
Because it's a.
It's not a synchronous call. How do you know it's an ACK to your message versus an ACK to somebody else's message?
Yeah.
Because it's an RPC call. The ACK is basically what I did is I have a ACK method on the client, not the client side. It can be maybe a slave object, and this is a relayer. And every time if the client send a message, it's a pass through the slave to send to the master, and master send to the relayer.
Right, relay relays it back.
And the relayer knows nothing about the ACK, so the master ACK back call this ACK method remotely and sending the sequence number back.
Right, but how do you know it's your sequence number or somebody else's sequence number?
I don't need to know, but master knows.
Yeah, but is that sequence number sent to other people also? Supposing there are two clients.
No.
What if there are two clients?
I mean, this is assuming this is the broadcast request,
Yeah.
and this sequence number is just for that.
So a special message is sent back to the guy who sent
the broadcast request, and then the next message the
will be the relay message.
Yeah, the relay message has a new sequence number.
So what you're saying is that somehow the sending guy gets two messages back.
Yeah.
Okay. So and another way to do that, I mean, you can just send a message ID also, right? So you can wrap message with unique ID, host and local sequence number, and you can figure out whether you received your message back.
Yeah, that's nice. It reminded me of that day where we were having the discussion about going through the layers or just having remote objects.
Yeah, I wouldn't recommend you make the method calls. Huh? You can get into a recursive loop there, because that will go back. The filter object calls a remote method call, which goes back to the filter object, which can cause another method call.
Well, it depends on
But you don't need to. You don't need. Yeah.
Okay, so just I would recommend you don't do it. And if you're going to do this algorithm, I would do this. Okay. So when the okay, and so in this distributed algorithm, assuming that you're off by only one, okay, which is a strong assumption here, you just choose the maximum received message and send it back, okay. And now the question is, do you send it, do you send back the maximum message to all the clients, or do you send it only to the clients who don't have that message, assuming you're off by only one? So depending on which way you go, you may have to go and change your algorithm here to go and discard messages that are duplicates. Okay, so there's a possibility in both the algorithms, the local buffering and the global buffering message algorithm, local buffering with bounds and the global buffering with sort of no bounds, that you may get messages out of
So this should be done by the filter, but not the application itself, right?
for the filter.
Yeah.
Absolutely, yeah. Okay. So key idea: synchronous systems, passive replication. You've got this architecture. There is this notion of partial versus complete broadcast. If we just assumed complete broadcast, things would be even easier. Okay. Distributed versus replicated buffering, and again, this is off by one or off by arbitrary amount. Okay. And we could have had an algorithm where we actually made a remote function call for the broadcast. We could have done a synchronized also. That's another way we could have done it, where we use that call that I told you about, the function call, to sort of just synchronize everybody, and in which case the algorithm I showed you, distributed algorithm, would work. Okay? But if we allow that to be void, which is what we have in the implementation, then we would need replicated buffering.